Hi there, and welcome to this senior physics video on light and waves. In this video we're going to look at critical angle and total internal reflection. Now we all know that when light passes from one medium to the next that the speed is changed. Now generally what happens is if it's moving from a more dense medium into a less dense medium, the refracted ray is going to move away from the normal. Remember, the normal is always at 90 degrees to the boundary surface. So if this is the boundary surface, say water underneath, and I've got air on top, the normal is going to sit at 90 degrees. Any light coming from the less dense medium into the, from the more dense medium into the less dense medium will be refracted away from the normal. So if you look at the example we've got down below, we've got a media, it doesn't matter what it is, but the media is more dense than the air above it. So we've got in diagram 1 there, we've got an incident ray shown in green coming through and it's at 90 degrees. Now when it hits the boundary surface at 90 degrees, we know it passes straight through. Its path is unaltered, even though its speed changes. In this case, the speed will quicken up. Now let's put an incident ray coming in at an angle theta I to the normal. Now, because it's coming at an angle, as it hits the boundary surface, it's going to be refracted, theta r, and it's going to move away from the air. Now, if I make that angle of incidence greater, as you can see in diagram 3, the angle theta r gets greater, till eventually what happens, we reach an angle where we're going to produce a refracted angle which hits at 90 degrees and runs along the surface of the actual boundaries between the two media. Now, if you were to look at this, you wouldn't see anything at all. Basically, what this point is it's that point where you get the glare off the water, you get the sheen, you get no reflection, because basically light is coming straight across the surface of the water and it's hitting you in the eye. Now, this angle is very, very important, especially for our next concept that we're going to look at, which is total internal reflection. Now we can calculate the critical angle of a medium by basically using Snell's law. Now the critical angle we're going to assign the symbol theta c, critical angle, sort of stands to reason. So here's my Snell's law. So I've got the refractive index of the medium times the sine of the incident ray. In this case, the incident ray is going to be theta c, or the critical angle, will equal the refractive index of the second medium, where the light is moving into, sine 90 degrees, because remember the refractive ray is going to be passing along the surface of the medium. So the thing to understand is that sine 90 always equals 1. So in truth, to basically work out the critical angle of a specific media, we need to know the refractive index of the media, and we know that it's going to be passing into air. So we know that air, in this case, is going to be 1. If it happened to be another medium, then obviously we'd need to know that refractive index. Note that it's got to be moving from a more dense into a less dense for the refractive angle to actually go down along the boundary surface. If it's moving from less dense to more dense, remember it's going to move towards the normal. So bear that in mind. Okay, well let's have a look at an example and see how we can use it. So we want to find the critical angle of a beam of light coming from water whose refractive index is 1.33 going into air. So let's write down what we know. Well, we know the refractive index of water is 1.33. We know the refractive index of air is 1. And we know that sine theta r will equal 90 degrees. So the refractive ray is going to be 90 degrees. And we want to find theta c. So we know that M media sine theta c will equal N air sine 90 degrees. So replace what we already know. So 1.33 times sine theta c will equal 1. So I'll move the 1.33 to the other side. So it'll be sine theta c equals 1 divided by 1.33. Once I've calculated that, I then do sine to the negative 1 to find theta c, and the result is I end up with 48.8 degrees. So that is the angle which light has to be shone at to the normal as it's emerging from a medium. As it passes out, it will produce 90 degrees on the boundary surface. Now, total internal reflection is what happens when we go greater than the critical angle. What happens to the refractive ray as we go greater than the critical angle? Well, the thing is, the laws of reflection then apply. The angle of incidence to the normal will equal the angle of reflection to the normal. The boundary surface acts like a mirror. The light hits the surface, but because it's trying to be refracted, it's refracted so great, excuse me, it's refracted so great, it's actually bent back into the water. So let's have a look at an example. So here is my critical angle. You can see theta c, my critical angle, is producing a refracted ray of 90 degrees. But if I go greater than theta c, we then get the diagram, our second diagram on the right there, where we've got theta I equals theta r. The result is that the light passes off the surface of the mirror, off the surface of the boundary, and acts like a mirror and bounces back in. Now, how is that useful? Well, we use it a lot for telecommunications. When we convert an electrical signal into light, we can pass it down fiber optic cables. Now, the beauty about fiber optic cables is that the light passes through and it's not lost. Now, the old copper cables that used to carry things like telephone messages, the sound used to be dissipated into the surroundings. And for example, you could actually go down, if you happen to be scuba diving near a telephone cable, you could actually go down and listen to the message going on. So thank you for watching, and I hope you join me again.